it was to +1, the greater the direct variation we had. And the closer it was to -1, the greater the inverse variation we had there. Okay. Today, we're going to work with the regression line, which is a linear algebraic equation. We're going to show you how to find that least squares regression line. So the idea behind this, ladies and gentlemen, is if we have a linear scatter plot, ideally speaking, we would like to fit a line to the data. And that line is going to be called the regression line, or it's called the line of best fit. And this regression line is made possible thanks to differential calculus. But we don't have to do differential calculus to appreciate how this and what this line can do for us and where it comes from. Ultimately, when you find this regression line or this best fit line, you can use it to make predictions. Okay. And this is an example of a scatter plot. These little blue points are the ordered pairs that were collected out in the field that pertain to some something. And then we basically fit this line to these data points here. This line here is called the regression line, or the least squares regression line, or the best fit line. And if we look at the difference between the actual y values and the predicted y values using this regression line, and by the way, y prime here, this little symbol here on y is y prime. Y prime is the predicted value of y, whereas y is the actual observed value of y that we collected in the field, okay? You can see that some of these points are very close to this best fit line or this regression line, whereas some points are quite far away from it. But if we look at the difference that exist between the predicted y values and the actual y values of each of these points, those differences are called residuals, okay? So a residual is the difference between the actual y value and the predicted y value if you were to use your best fit or regression line. The farther the point is away from the line, the greater the residual or the greater the error exists between the actual y value and the predicted y value. This point right here lies exactly on the best fit line. So there would be zero error between the actual y value and the predicted y value for that point. In other words, the residual for this point would be 0. Okay. So these differences, again, that exist between the actual y value and the predicted y value are called residuals. Now, how are we going to find this magic line, this so-called best fit linear regression line? Well, this is its equation here. Y prime is equal to a plus bx. Or you could spin these terms around and put this in the slope-intercept form, in the form of y prime equals bx plus a. At any rate, b is the slope of the line. This is the slope of the regression line, b, and the y-intercept, where the line crosses the y-axis, is going to be a. This is your y-intercept. Now we got to be careful because traditionally in algebra, our slope-intercept form is y equal to mx plus b, where b normally is the y-intercept in algebra. But in this course, a is the y-intercept, and then b is the slope of the linear regression equation. To find a and b, we use these formulas here. And notice to find a, we're going to need to know the sum of y, the sum of x squared, the sum of xy. And we're going to need to know the number of observations or ordered pairs we collected. To find b, we're also going to need to know all these summations here. So obviously, to do this problem manually, to find the slope and the y-intercept of the regression line, we're going to have to maybe use a table to help us compute these intermediate results that are needed. These equations are called normal equations, and they come from or are derived from using differential calculus. Okay, these are called normal equations. The beauty of this is we don't have to go through differential calculus to see where these things come from. You just basically take it on trust from what I'm saying, and we're going to just learn how to use or compute these values and then put together our linear regression line for predictive purposes. All right. Knowing where these come from is beyond the scope of this course unless you've had some calculus. All right. Here's an example to breathe life into all this. We previously used this table of the heights and the number of stories of several buildings. Do you remember that example? That was a little ways, but that was last week. To find the correlation coefficient between these two variables, we made this table. And of course, we added on these columns. And then at the bottom, we summed up all these columns. The sum of the y values, the sum of the x values, the sum of the xy, sum of the x squared, sum of the y squared values. We needed these summations in order to compute the correlation coefficient. Well, ladies and gentlemen, we're also going to need these summation values to compute the regression equation also. As you can see that there's plenty of summations in computing the slope and the y-intercept of this equation. Recall that the Pearson linear correlation coefficient of this bivariate data set that we worked with last week was 0.927, which means there's a very strong positive linear correlation between the number of stories that a building has and its overall height. Okay. And we also conducted that t-test at 5% to further convince ourselves that there is a significant correlation between x and y here. All right, so let's see if we can find or compute the linear regression equation for this ordered paired data set here, where x is the height of the building, the number of stories the building has is the dependent variable y. Well, as we got to substitute in our summations where they belong into these formulas here. So we get those summations from this table back over here, okay? So in for the sum of y, we substitute in 351. In for the sum of x squared, we substitute in this big old number here, this 300,700,051, et cetera, et cetera. Notice we had, was it 6 ordered pairs there? So n is 6. Anyways, you get on your calculator and you dial these up, and you will compute the y-intercept and the slope of this regression line. So it appears that the slope is 0.0897 and the y-intercept is about 5.375. Okay. So lo and behold, you now have your linear regression equation that basically minimizes the sum of the squared residuals. Okay. So if you were to take each of these residuals and square these differences between the predicted y and the actual y values, and you were to sum them up, you have what's called the sum of squared errors. Well, there's a linear regression equation is called the best fit line because, or sometimes it's referred to as the least squares regression line, because it minimizes the sum of these squared errors or residuals. So it is the best line that you could possibly fit to your ordered paired data set. There is no line that fits the data better than your least squares regression line. And that's guaranteed by differential calculus. All right, so this is our best fit line for this ordered paired data involving the number of stories a building has versus its height. You cannot do better in fitting any line that minimizes your sum of squared errors any more than this line here, because stop and think, in reality, there's a lot of lines you could fit to this ordered paired data. There's a line with a certain slope. There's a line. Here's a line. Here's a line. Here's a line. There's an infinite number of lines you could fit to these ordered paired data points. But the one that minimizes sum of square errors between the predicted y and the actual y values is the best fit equation, or the least squares regression equation right here. That's the optimal line that you could possibly fit to those data points. Okay. And you can see that it is quite a quite good fit. Most of these data points are very small, are very close to the line, if not on the line. You know, you got one that strays quite a distance away from the line, so this residual would be significant. But all these other residuals would be basically what? Trivial in size. Do you agree? And look at these points. They actually lie on the line, so you have a perfect prediction of these y coordinates here by this best fit linear regression line. So to that one. So that's the best fit line. Now, that's how you would find this linear regression line manually, by using those normal equations and using all that computed summation notation. Okay, but is there an easier, quicker way? And the answer is there certainly is. It's called our TI-84 calculator. And the TI-84 calculator can perform linear regression within about a fraction of 1 second. Right? And so I'm going to show you how to find this linear regression equation using our TI-84 calculator now. To do that, we have to go back to our raw data set. And therefore, we're going to type in our X and Y ordered paired data into list 1 and 2 respectively. So let's go get our calculator. All right, stat edit. Type in the X data in list 1. And the Y data in list 2. Thankfully, we only have 6 ordered pairs to type in. Most data sets have thousands or millions of data points, in which case you would be a while doing this. In which case you'd have to turn it over to a computer system and a statistical software package. There's a lot of stats programs out there, Minitab, Systat, popular ones. Microsoft Excel can do a little bit of a statistical analysis too. And it can also make scatter plots. It can also compute your regression equation. All right, so I've loaded up list 1 and 2 with the X and the Y coordinate data, respectively. Now that we got our list loaded up, second mode to quit. Go to stat. Oh, you know what? I want to make sure that my R and R square values are reported. So I'm going to go to mode. And I'm going to make sure that my stat diagnostics feature is turned on. Presently, it's turned off. I'm going to toggle it on. You need to turn this feature on if you want to see R and R squared reported when you do regression. So leave that on. We go to stat. Okay. Calculate. Then to perform linear regression, we go down to lin reg. Right there, linear regression. Hit enter. X and Y list must be list 1 and 2 respectively. If they are not, you're going to have to force in the names where they belong. X1 is L1. Y list is L2. Now, go down here and hit enter on calculate, and you'll see your linear regression equation surface. Notice the A and B are just the opposite of what your author's using in your textbook. Just the opposite. So what they call A in your textbook, which is the y-intercept, on your calculator, A is the slope of the linear regression equation. And in your textbook, B is the slope of the linear regression equation. Well, on your calculator, B is the y-intercept. So notice the roles of A and B are reversed between your textbook and the TI-84 calculator. At any rate, you can see that for a, or I should say for the y-intercept, we do get the 5.735. For the slope of the regression equation, we get 0.0697. So that's how you generate your linear regression equation. So therefore, y prime is going to be equal to about 0.0697x plus 5.3.5 plus 5.735. Notice the correlation coefficient is 0.927. That's the same as what they have on here. All righty. Any questions how we did that? All right, now I'm going to show you how to not only create the scatter plot, but also compute the regression equation and overlay the graph on top of your scatter plot. To do all of this, we go into stat plot first. Second, y equals. We'll turn the stat plot 1 on. Select the scatter icon, scatter plot icon. X and Y list must be list 1 and 2 respectively. Looks like I'm all set here. Second mode to quit. Now let's go back to stat, calculate linear regression. Stat, calculate lin reg. Make sure the names of your X and your Y data lists are where you put the data. Leave the frequency list blank. Go down to store regression equation. I'm going to store my regression equation in Y1. To access that, I hit my vars key. V-A-R-S. Go over to Y-vars. Select function, edit. Select Y1 by hitting enter. And then go down to calculate. All right. Now, ladies and gentlemen, if you take a peek at your equation editor, y equals, you can see that the regression equation has been pasted into Y1, just like I told the calculator to do so. So second mode to quit. All right, just go to zoom. Zoom stat. And not only are you going to see the scatter plot, but you're going to see the graph of the best fit linear regression line overlaying your scatter plot. And there it is. This point seems a little bit far away. Let me see something here. 0.0698 735. There's going to be a little bit of a discrepancy here. Difference here. Notice they don't even have the X in their equation here. X should be right here next to this. All right. But I'm going to make sure that I typed in my data correctly. Oh, I lost all my data. Okay, so you can see how we constructed this linear regression equation by using the lin-reg function on the calculator. How we made the scatter plot and overlaid the graph of the regression equation on the scatter plot. So you can see that in general, most of these points fit the line quite well. Some points wander a little bit away from it, but in general, it's a pretty good fit here. Okay. Now we can use the regression line to make predictions as long as a few things are true. Number one, the points of the scatter plot are close to the regression line. That's obvious. I mean, if your points, your ordered pairs are far away from your regression line, then maybe you chose the wrong regression. Maybe you should be using some other sort of regression. For instance, if your scatter plot kind of looks like maybe they belong on a parabola, then maybe you should do what's called quadratic regression. Or if it looks like your points or ordered pairs you collected, if it looks like the scatter plot belongs on the graph that is periodic or cyclical, then maybe you should have done what is called sine or cosine regression from trigonometry. So it really depends on how your scatter plot looks as to what type of regression you would subject it to. If it looks like most of the points, if not all of them, lie very close to being on a line, then you would want to perform linear regression. Okay. Now, another thing is the value of R is significant, which means that when you conduct that lin-reg t-test that we did last week, that we're able to reject the null hypothesis and conclude that rho is not equal to 0. That's what this is saying, to say that R is significant. Now, this is also very important too. The value of X that is used to make a prediction has to be within the range of the values of X that was used to build the regression equation. Okay, what's that saying? Let me show you what that's saying. This is very important here. In other words, let's say you came up with a regression equation whose graph is like this right here. Okay. Let's say the maximum data point that was in your data set, your maximum X coordinate of that data point was, let's say, 20 here. X is equal to 20. And maybe, you got some other data points kind of scattered around this thing here. All right. The bottom line is this, ladies and gentlemen, if the range of your X data, let's say the range is from like maybe 5 to 20. How much faith would we put if we were trying to make a prediction using our linear regression equation by putting, let's say, 30 in for X? Where 30 is way out here. Do you agree? How much faith would we have in that prediction there? The answer is we would not have much faith in that at all. Here's why. Yes, between 5 and 20, it does look like our data is linear. Therefore, that would warrant the building of a linear regression equation to try to fit it. But how do we know beyond 20 that our relationship between X and Y remains linear? We don't know that. It's a huge question mark. All of a sudden, maybe this relationship becomes maybe quadratic in nature, or maybe it becomes exponential in nature, or maybe it becomes periodic in nature. We don't know. We don't have a clue what's going on beyond 20. And because of that, ladies and gentlemen, to assume that this relationship continues to be linear beyond the largest X coordinate of the rightmost data point that was used to build this regression equation is a very dangerous and faulty assumption. You would not have much faith in making a prediction for this. Now, would you have faith in making a prediction for any X value that lies between 5 and 20? The answer is yes. You would have as much faith as your R or R squared value indicates to you as the the quality of how well that line fits the ordered pair data. So you never want to extrapolate beyond the range of the X values that were used to build a linear regression equation to make a prediction. That's a very dangerous thing to do. Does that make sense what I just said there? Yeah, so long as you stay within the range of the X values that were used to build a regression equation and making predictions, you can take good faith, you can have faith in those predictions. If you go outside of that range, don't try to make predictions. It's anybody's guess, ladies and gentlemen, as to how accurate or inaccurate your prediction is. Not a wise thing to do. All right, if R is not significant, which means that maybe we were not able to reject the null hypothesis where rho is equal to 0, maybe, the best predicted value of Y for any value of X is the mean of the values of Y in the original data. In other words, if R is very close to 0, your correlation coefficient, then, ladies and gentlemen, what you'd want to do then, in that case, is to make a prediction for Y for any value of X. Your best predicted value then would be the mean of all the Y coordinates of all the ordered pair data that you collected, okay? In that situation, your best predictive, or most accurate predictive value for any value of X would be the mean of all the X coordinates, all the points. That's if R is not significant, meaning that it's close to 0, meaning that there's not a good linear relationship between X and Y at all. Or meaning that you were not able to reject the null hypothesis of your linear regression t-test that we looked at last week. All right, the sample needs to be random. That's obvious to prevent or minimize bias. For any specific value of X, the values of Y are normally distributed about the regression line. The standard deviation of the dependent variable is the same for each value of the non-dependent variable. Okay. If these assumptions are approximately true, then your regression equation is of value. So suppose we use our linear regression equation that we developed a couple slides back for the buildings. Suppose we want to make a prediction. If we know that a building is 800 feet tall, what would be the predicted number of stories that it would have? Well, you would literally let X be equal to 800. And therefore, to make a prediction of the number of stories, we put 800 in for X into our linear regression equation. And then we just crank out the value, which would be 61 stories, would be the predicted number of stories for a building that has a height of 800 feet. Okay. And notice that 800 is within the range of the X values that was used to build this regression equation. You can see the X values range from about 501 to 1136. So you can see 800 is in this range. And so you would have a fair amount of faith in that predicted number of stories for a building that's 800 feet tall. Okay. But if you try to make a prediction for a building that's like 3,000 feet tall as the number of stories it has, then we would not have much faith, if any, in that predicted value. Okay. All right. Now, the slope, how would we interpret what this slope of this linear regression equation is saying here? Well, it means, ladies and gentlemen, if the height of the building increases by 1 foot, then the number of stories that the building has would increase by 0.0697 stories. All right, make sense there? Okay. And this is just indicating the fickleness or the error in trying to use your regression equation to make predictions outside of the range for the x values that were used to build a regression equation. So you can make these regression equations to help you make predictions, but you have to use them with a little bit of common sense too. You should not be predicting for x values that are outside of the range that was used to build the equation. Okay. All right, this is basically just walking you through some of the routines that we've seen on our calculator there. All right, conducting a t-test. All right, storing the regression equation, doing the scatter plot and the graph of the regression equation, overlaying the scatter plot there. And this is the t-test we conducted last week, the linear regression t-test for testing for the significance of the correlation coefficient, whether it is or is not equal to 0. And that tells us basically the strength of relationship between what we have between x and y. All right, so let's go to our textbook and see if we can do a problem here. Okay. So let's go to our textbook. We'll maybe do a problem. You're out of section 10.2. Entitled regression. All right, here's a good example, number 11. For random selection of drivers, their ages, and number of automobile accidents they had over a 3-year period are shown. I think we seen last week that there's a pretty strong correlation between what was it? Was it a direct correlation between age and number of accidents, or inverse correlation? Anybody remember? From last week. Remember we computed the correlation coefficient for this data set?
I believe it was direct.
So that if you say direct, then that would be saying like, if the age of the driver increases, the number of accidents they have would increase also. Was that the case?
It was the older the driver is, the less accidents they have.
So that is, I think it was in an inverse relationship. Do you agree? The fewer years of experience a driver has, the more accidents they tend to have, versus the just the opposite. The more years of experience of driving, the less number of accidents. So I think R was pretty close to -1. Was that correct? I think. Does anybody have that in your notes for that problem? I believe R was very close to -1, which indicates a fairly strong inverse linear relationship between age and number of accidents here. All right, so what are we going to do with this problem here? Well, ladies and gentlemen, what we could do is maybe we could just use our calculator to compute the linear regression equation for this. So, you know, you want to put your, what's your X and what's your Y data here? What would be your dependent variable and your independent variable, or your response variable versus your explanatory variable? Anybody know what would be what here? What would be X and what would be Y?
Age would be X.
Let's see. Yeah, you're right. Age would probably be the independent variable X, and the number of accidents you have, Y, would depend upon your age. You are correct. So let age be X, accidents Y. Go ahead, put the data in like lists 1 and 2 respectively, and do linear regression. I would also like your calculator to report R and R squared. So please do turn on your stat diagnostic feature. Turn that on by going into your mode setting. That's a one-time thing you got to do. And see if we can find a regression equation. All right, go ahead and do that. That'll be called classwork number 1 here. Just try to find a linear regression equation for this thing first, okay? All right, so for number 11, let's take a look here. You can do this on your calculator. All right, so our age is X here. And then Y is the number of accidents. All right. So when you, if you want to do regression, again, make sure that your stat diagnostics feature is turned on if you want R and R squared to be determined here. Now you go to stat, calculate linear regression. And there's your linear regression equation here. So your linear regression equation is going to be, this is your prediction equation, so it's going to be Y prime. So where is my, oh, here we go. So Y prime of X, this is your linear regression equation here, is going to be equal to this linear equation, the slope of which is going to be so the slope is going to be negative 0.1801 X. I'll round off to 10 thousandths place, 4 decimal places. And your y-intercept is going to be okay. So that's your linear regression equation. Did anybody get that equation there? Anybody get that linear regression equation?
Yep.
Yes.
So we got that. You can see that R is negative 0.2, negative 0.92, which means that R is very close to -1. So we have a very strong inverse linear relationship between age and number of accidents. That indicates that if one variable goes up in value, the other one goes down and vice versa. And that indicates that as the age increases, the experience of driving increases, the number of accidents tend to go down and vice versa. All right. Now, another thing is we can do a scatter plot here. If you go into stat plot, turn plot 1 on, and you can configure it to make a scatter plot here. And another thing is when you do regression, you might want to store your regression equation in Y1. To get to Y1, you hit your vars key, go over to Y vars, select function, and select Y1. That'll not only compute your regression equation, but it will then store it in your equation editor for Y1. By doing that, then you'll be able to graph or overlay your regression equation on top of your scatter plot. So hit calculate. And then just hit your zoom button and go down to zoom stat. And you should see your scatter plot along with your linear regression equation line over line. There it is. Notice you do have some residuals here, some differences between the predicted y and the actual y values. Some of these points actually lie right on the line like this. This is a perfect fit here. But in general, you do usually have some residuals or some errors between the predicted y and the actual y values. All right. This linear regression equation, though, minimizes the sum of these squared differences between y and the predicted values of y. This line minimizes that error, if you will, in general. That's why it's sometimes called the best fit line or the least squares regression line, because it minimizes the squares of these residuals. And we'll see that a little bit in the next section. Now, I remember I also stored this regression equation in Y1. And so we can use that to make a forecast or prediction. For instance, they want to know what would be the predicted number of accidents for a driver that is 30 years old. Well, to do that is pretty simple now. Pretty simple to do. Let's clear our screen. Let's go to vars, go over to y vars, stay on function, hit enter, and select y1. Open parenthesis, and now all you have to do is type in 30. What your calculator is going to do is it's going to take 30 and it's going to feed it in for the x variable into the linear regression equation, multiply 30 by the slope, and then add the y-intercept to crank out the predicted number of accidents. Your calculator is going to do this all behind the scenes very quickly, because remember, we told the calculator to store a regression equation in y1. Hit enter, and there would be the predicted number of accidents for a 30-year-old, about 3.6. Now you can bring this entry back up. Second enter brings the entry back up, and you can then make a prediction for some other age. Maybe if somebody's like 37 years old, what would be the predicted number of accidents? There you go, about 2.4 accidents. Go back and get the function. And suppose we had somebody that was, now, would you have much faith in this prediction if I wanted to know how many accidents a 65-year-old would have? Why or why not?
65's not in the range there, so.
Yeah, 65 is way outside of the range of the X values that were used to build this linear regression model here. And because of that, you would not have much faith in going outside of that range and trying to make a prediction, because we don't know for sure if after X equals what, 50 years of age, we don't know if this relationship continues to be linear. All of a sudden, it could be suddenly become nonlinear in some nature, in which case trying to use a linear equation to make a prediction of something that's no longer linear after the age of 50 would be worthless. And so be careful. When you make predictions outside of the range of X used to build a linear regression equation, you almost have to take it as a grain of salt, ladies and gentlemen, because you don't really normally have much faith in such a prediction. Okay. All right, but this is pretty neat how we can make predictions for any age within our range, which is between, it looks like 21 to what, 50 years of age. So like we could predict the number of accidents, maybe like a, I don't know, maybe like a 47-year-old might have. Okay, type in that. That's well within the range of X. And they would be expected to have about, what, maybe a half of an accident? That probably just means half of your car got smashed, correct? No, I'm just kidding. That's on average. So we would say on average, all 47-year-olds would be expected to have, on average, 0.6 accidents. That's an average, okay? All right, so linear regression, pretty neat. Pretty darn neat to have that go like that. Now, I have a question for you. If I had a scatter plot, suppose I had a scatter plot that looked like this. All right, I'm just going to throw some data in here, just for illustrative purposes here, to illustrate something important. Okay, suppose my, my X data is like maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Suppose my Y data, my Y coordinate data is like let's say 1.5. Okay, maybe 4.1, 8.8, 15, 24, 37, let's say 49, maybe 64, maybe 78.5, and maybe this is like 99.1 or something. Okay. All right. Let's go make a scatter plot with this ordered pair data set. Suppose we collected this out in the field here. All right. Let's go ahead. Second Y equals plot 1. Make sure it's configured for a scatter plot. All right, let's do this. Hit zoom button and zoom stat. Let's make a scatter plot. All right, you know what? I forgot to clear out the regression equation from the previous problem. So I'll go to Y equals and hit my clear button. That clears out Y1. All right, let's do that zoom stat thing again here. All right, there's our scatter plot. Now I have a question for you, ladies and gentlemen. Does it appear that these points lie on a line?
No,
No. And because of that, just by looking at the scatter plot, I think it would be futile to conduct a linear regression on such a data set. It looks like we would probably want to fit some other sort of graph to this data. Can anybody maybe guess as to maybe what would be a good fit? What type of function we should try to fit to this as opposed to a linear function?
it's a logarithmic function.
Yeah, I don't know. Maybe if it's flipped around and reflected about an axis, it might be. But doesn't this kind of look like half of what opening upwards, half of something opening upwards? What do we call that graph? Half of a. Well, it starts with the letter P. Half of a
Parabola.
parabola opening upwards. And parabolas come from what kind of functions? Do you remember? Anybody from algebra? What kind of functions generate parabolic graphs? Starts with the letter Q.
Quadratic.
Quadratic functions. Yeah. So, it seems like in this particular situation, ladies and gentlemen, we would not want to do linear regression here. It looks like maybe we can, do quadratic regression to maybe model this data according to a parabola. Okay, let's go see. Let's go to stat, calculate. Instead of linear regression, maybe we want to perform what's called quadratic regression right there. Quad reg is short for quadratic regression. All right. Notice X data, Y data, list 1 and 2. We can store the regression equation in V1, excuse me, Y1. So we get vars, Y vars, function, Y1, calculate. And would you believe there is our quadratic function that's generated? A is the leading coefficient, which is about 0.98 times x squared, plus the linear coefficient is 0.016 times x, plus the constant term of this quadratic function is about 0.093. Okay, now, here's what we're going to do here. We're going to do the scatter plot, and we're going to overlay our graph of our quadratic function or quadratic regression equation to see what kind of a fit it appears to be. It appears to be fitting the data points quite well. Do you agree? that looks like the model you should be trying to use to model this data, not a linear regression, but a quadratic regression curve. So your scatter plot can really direct you in the right, direct you accordingly as to what type of regression to perform. And there's the beautiful things about this calculator is it can do quite a few different regressions. It can do linear regression, quadratic regression. It can try to fit a third-degree polynomial function to a scatter plot if the graph is in the form of like a cubic type plot. In other words, if you had a scatter plot that kind of looked like this, then, ladies and gentlemen, maybe you want to fit like a third-degree polynomial function to it. That's called cubic regression. Everybody see that there? Or you have quartic regression. Quartic is trying to fit a fourth-degree polynomial to a scatter plot. If that was the situation you were, up against. Okay. We also have, I don't know why they have this other linear regression function here. Notice they have it appearing twice. For the life of me, in all these years, I still don't understand why they put another one there. We don't use this one. Just use this one above. Okay. Now, you could perform natural log regression. The graph of a natural log function tends to look like this. That's the graph of a natural log function. So like maybe, your scatter plot had a signature that kind of like mimic, this type of curve, if you will. In which case you might want to try to do natural logarithmic regression. Okay. You have exponential regression. Maybe your scatter plot's really taking off very quickly here. Maybe it's modeling an exponential function. Exponential functions grow very quickly. Maybe you want to model it according to an exponential function. You could try that. Let's see, any other types of regressions here? Let's see, we have power regression, logistic regression, and sign regression. For instance, suppose that you were modeling like the monthly average temperatures for a particular place during the course of a year. Well, as the seasons change, ladies and gentlemen, you can see that your temperatures tend to maybe max out in the summertime. Do you agree? And come on back down and what? Min out in the wintertime. And then we go into the next year and they tend to what? Max out again the next summer. And maybe min out again. Maybe your scatter plot has, a periodicity to it where it tends to repeat in cycles, in which case you'd probably want to maybe try to fit a sine or a cosine wave to this to model it accordingly. And that's trigonometric regression, okay? So we don't just have linear regression on here. We have all different types of regression. So just keep that in mind if you ever collect ordered pair data. Take a look at the scatter plot because that will direct you as to which regression you might, or kind of curve you might want to try to fit to the data or should fit to the data. Right? Obviously, if your data is, expressing some sort of a linear signature, then you want to perform what? Linear regression. I mean, why would you want to try to perform sign regression on something like this when it's clearly like a linear signature? You want to do linear regression in that case. Okay. So this calculator is pretty amazing in that it offers you many different types of regressions you could perform, not just linear regression. So that's a pretty cool feature there. Okay, just thought I'd point that out. All right. Okay, and here's a lot of practice problems in this textbook here. Having you do linear regression on different ordered paired data sets. And let's see. Okay, so do we understand how to do regression on our calculator? to find a linear regression equation and how to find R and, okay. All right. So that's how you would perform regression using your machine here. All right, let's go to the last section here. This is a fairly short section. All right. This is just going to look at another measure of how well our model fits our ordered pair data set. It's called the coefficient of determination. And I've been kind of alluding to it all along here. It is the R squared value that is reported on your calculator just after the R value is reported. And R squared literally is the square of your linear correlation coefficient. Okay. And we're not really going to worry about prediction intervals in this section. The most important thing is this coefficient of determination R squared, how to interpret what it's saying. Okay. All right. Suppose we have this simple linear regression model here. Here's our ordered pair data set. And we do linear regression on it. And we get a linear equation, which is y prime equal to 4.8 plus 2.8x. And notice the correlation coefficient R is 0.919, which suggests we have a very strong linear direct correlation between x and y. Now, the total variation, the total variation, which is the sum of the squared differences between the actual y values and the mean of your y values. Okay, remember they said like when the correlation coefficient R is close to 0 or is not significant, that y bar, the average of the y coordinates, is the best prediction you could make for any value of x. Okay. So we call this the total variation when you take the difference between the actual observed y values of your ordered pairs and the mean of the y values, and you square those differences and sum them up. That's called the total variation. Now, the total variation consists of something called explained variation and also unexplained variation. The explained variation is going to be the sum of the squared differences between the predicted y values from our best fit linear regression line and the average of the y values, y bar. That's called the explained variation here. Because that variation is explained by a regression equation that we actually modeled from the ordered pair data. Now, on the other hand, we have something called unexplained variation, which is the sum of the squares of the differences that exist between the actual y coordinates of our ordered pairs and the predicted y coordinates of our regression equation. Okay. You see, when you compute y bar in this other summation above here, that's the average of your y coordinates. And since that is the best predicted value for y for any value of x, even if r is very close to 0, we call this the explained variation here. Because y bar is the best predicted value for a lousy correlation coefficient of r, and certainly would also be the case if your value of r was very close to 1, you would have a very strong explained variation. Unexplained variation occurs because of the differences that occur between the actual y coordinates and the predicted y coordinates. The predicted y coordinates come from using the linear regression equation here. And your line of best fit is a good fit for your ordered pair data, don't get me wrong, but it's not a perfect fit. And because of that, you do have some unexplained residuals or variations that occur with these differences between the actual y and the predicted y values. Things that we cannot explain or control, things that are attributed to other factors that we're not maybe incorporated into this modeling scheme here. Okay, so this total variation is a sum of the explained variation and the unexplained variation. And you can see diagrammatically here, if I blow that up there, you can see the total variation, if you're to take this point up here, XY here, right up here. The total variation is the difference between the actual Y coordinate of this point right here and Y bar. So the height of this vertical dashed line, the length of this vertical dashed line is called the total variation. That's equal to the unexplained variation, which is the difference between the actual Y value and the predicted Y value, which lies right on this prediction line here. Your least squares regression line is this line right here. Added to the explained deviation, which is the difference between the predicted Y value and Y bar. Okay, so you can see the total variation is the sum of this error here added to this error here. All right. Okay, so. And you can see it represented up here. The total variation is the sum of the explained and the unexplained variation here. Now, when the correlation coefficient is close to 1 or -1, the actual and predicted values of Y tend to be very close to each other. Do you agree? Y minus Y prime tend to be approximately 0. These residuals approximately are 0 when you have an extremely good fit, when R is very close to 1 or close to -1. Therefore, the unexplained variation is very small, because essentially Y and Y prime are pretty much the same. And most of the total variation then is attributed to the explained variation, difference between Y and Y bar, okay? On the other hand, if the correlation coefficient is close to 0, which means essentially we have a very poor fit, linear fit with our regression equation, the predicted values of Y and the difference between Y and Y prime tend to be very large. In which case the explained variation is small, but most of the total variation is attributed to the unexplained variation in that case. So depending upon whether R is close to 1 or -1 or close to 0 will dictate which of these variations is the larger or more dominant variation and which one is the least dominant. And that ratio, if we take the ratio of the explained to the unexplained variation, we generate what's called R squared, which is the correlation, the coefficient of determination. All right. Now this last column here, this is a way of basically looking at the numeric sizes of these variations, where Y is the actual value of Y and Y prime is the predicted value of Y using the regression equation. And this third column is the square of the difference between the actual Y and Y bar. Fourth column here is the square of the difference between predicted Y values and Y bar. And the last column is the square of the residuals, the difference between the actual Y versus predicted Y values. So the sum of the last column here is 14.4. This is what I've been calling the sum of squared errors here. SSE sometimes is referred to. The sum of squared errors that exist between the actual Y values and the predicted Y values. Your linear regression equation minimizes this sum. That's why we call it the best fit line or the least squares regression line, because it provides the least value for the sum of squared errors between y and the predicted values of y. The actual values of y and predicted values of y. No other line you could fit to the data would reduce this value any lower than 14.4. And that's guaranteed by differential calculus, because the regression equation is the optimal line you could fit to a linear scatter plot. Well, this sum of squared errors is also called the unexplained variation that exists. The explained variation is always the difference between the predicted y values and the mean of all our y coordinates of all our ordered pairs. And you can see that the sum of these two variations here is equal to the total variation of 92.8. That's the total variation. We can also build what's called a residual plot, where we plot each y value against the corresponding x value. In other words, we plot each residual, the difference between the observed y, the actual y value, and the predicted y value, against every x coordinate of every ordered pair. And the bottom line is this: when you make a residual plot here, when you plot y minus y bar, y minus y prime for the vertical axis, and your x-axis is the x coordinates of your ordered pair data, the way you interpret this residual plot as far as the strength of linear relationship that exists between x and y is that if there is any pattern to these points, if it appears that these points, lie on a line or lie on a line in any way, shape, or form, if there's any pattern to this residual plot, then we would say that there does not exist a very good linear relationship between x and y. And for that reason, you should probably be using some other regression to try to fit the ordered pair data. You can see with this residual plot that it appears that there is a pattern between these plotted residuals here. Okay. There appears to be a pattern here, a linear pattern there. So that brings us to the coefficient of determination, r squared, which is the ratio of the explained variation divided by the total variation. So if you take the explained variation and divide it by the total variation, you generate what is called r squared. Now remember, r ranges between 1 and -1, correct? So if you square a decimal between 1 and -1, it's going to become positive. And because of that, r squared is always a decimal that ranges between 0 and +1. This is what r ranges between. This is what r squared ranges between. So if the coefficient of determination is close to 0, the model cannot explain the variation and is not useful for predictions. If on the other hand, the coefficient of determination is close to 1, then most of the variation is explained variation. And the model is very useful in making predictions. So if you have like a coefficient of determination of 0.845, we would say that about 84.5% of the total variation is explained by the regression line. And about what? About 15% is not explained by the regression line. Now, if R squared was exactly equal to 1, then that would be saying that 100% of the variation in the dependent variable is explained by the regression line, which means you have a perfect fit. Okay. So again, the closer R squared is to positive 1, the more significant of a linear relationship you have between X and Y. The closer R squared is to 0, that indicates you have a very non-significant linear relationship between X and Y. So by using R and R squared, R can tell us what type of linear relationship we have, whether it's a direct or inverse. R squared gives us an indication as to the strength of that linear relationship. R can also do that too. But R squared gives us the percent of variation of the dependent variable Y that is attributed to the variation in the independent variable X. And so this coefficient of determination is very helpful in using in conjunction with R to determine what type of linear relationship we have and also the strength of the linear relationship we have. Okay. So let's see what we got here. All right. All right. Let's see if there's any. So the only thing I'm really going to hold you responsible for out of this section here, ladies and gentlemen, is that coefficient of determination R squared here, which is the ratio of the explained variation to total variation. And just remember, the closer R squared is to 1, the stronger linear relationship exists, or the more accurate linear regression equation you have in explaining the data, as opposed to if R squared is very close to 0, that you do not have a very strong linear relationship or linear regression equation. And you should maybe think of performing some other regression on your data as opposed to linear regression. So those are the, so what we did today is we found out how to compute a regression equation. How to compute it, basically using our TI-84 calculator and using the lin-reg function. Now, I did not have you do that manually. You can see that it was rather tedious to perform regression manually in the sense that you had to use this laborious formula here, right here, these normal equations. And you can see that this would be very time consuming, especially if you had many ordered pairs. I mean, if your data set, numbered in thousands or the millions of data points, there would be no way in a humanistic way or humanistic manner of trying to come up with a linear regression equation that would have any accuracy to it whatsoever, because we are prone to making mistakes. All right. In which case you would probably, like I said, want to use like a software package on a computer and make use of the speed of the computer. All right, so when I assign problems out of section 10.2, all right, I will probably have you just doing regression using your linear regression function on your calculator. I mean, those are the normal equations. You can also perform this regression manually if you want, but we have the calculator at our disposal, and we're usually pressed for time. And for that reason, the lin-reg function, cuts through and circumvents us from having to go through the drudgery of using these normal equations here. Right? But there they are. And so I will open up section 10.2 on linear regression. And also, I might give you a question or two out of 10.3 regarding the coefficient of determination R squared. Okay. But there's not going to be really too much homework coming from 10.3. The bulk of it's going to be from 10.2. All right. So all we have left now is just 11.1. And let's take a quick peek at what that's going to entail. That's going to be, we're going to look at a couple of non-parametric statistical tests. Non-parametric means that the parent populations from whence the samples are chosen do not necessarily have to be normally distributed. They could be distributed according to some other distribution, in which case you need to use a non-parametric hypothesis test as opposed to what we've been using, which are parametric hypothesis tests, which require the parent population or populations are approximately normally distributed. We'll perform a chi-square goodness of fit test in 11.1. We'll perform a chi-square test of independence in 11.2. And then in 12.1, we will conduct what's called one-way analysis of variance for testing for the equivalence of more than two population means. The nice thing about analysis of variance is you can test to see maybe if 10 population means are all equivalent to each other versus they are all not equivalent to each other. That's analysis of variance. And we have a wonderful function built into our calculator called the ANOVA function. It'll take care of business in 12.1. And that will conclude a course in elementary statistics. Okay, so we're in the home stretch here. We don't have much going on here left. Just try to finish up the course. Don't take your foot off the gas pedal just yet, ladies and gentlemen. We got a couple more sections to go through and a couple more assessments. The chapter 10 and the chapter 11 and 12 exam, which will be opened up on the, let me see something here. 11, 12. Yeah, because I'm going over 12.1 on December 20th. So you have to see how the analysis of variance is conducted to take care of business in 12.1. But I will make sure I open it up promptly for you to get that done by midnight, December 21st. Okay. All right. And notice that the homework on 11.1, 11.2, and 12.1, 3 sections, will also be due by midnight, December 21st. But the axe falls then because I got to have grades in by the 22nd. All right. All right. If you have any questions or comments, you can stay on the line. I'll be on for a couple minutes. If not, have a great day. And we will get into some non-parametric statistical tests in 2 days. Okay. Take care.